Teaching Robert, mathematics lecturer at National Teachers College, Cavalry. So in this video we shall look at the distance of a point from a line, angle between a line and a plane, and the angle between two planes. To begin with, we shall look at the distance of a point from a plane.
In this video, we're going to talk about how to calculate the distance from a point to a plane. Now, before we actually solve the problem, let's talk about how we can derive the formula. So let's say we have some plane represented by this picture and a point above that plane. Let's call that point P1. So our goal is to find the distance between that point and the plane. We want the shortest distance. We're going to call that distance D. Now let's say we have some other point that is on the plane, which we'll call P0, and we're going to draw a vector emanating from P0 pointing towards P1. And let's call that vector B. Now let's turn this into a right triangle. Theta is going to be the angle between B and D. So with this information, how can we find D? Well, first, let's begin by defining vector B. B is basically P0 to P1. So it's the difference between those 2 points. P1 has the coordinates x1, y1, z1. P0 has the coordinates x0, y0, z0. So vector B is going to be x1 minus x0, comma, y1 minus y0, comma, z1 minus z0. Now, in order to define a plane, we need a point on the plane and a vector that's perpendicular to the plane, or the normal vector, which we'll call n. Now, in order to find the value of D, we need to get the scalar projection of B onto n. So I'm going to highlight that in green. So the scalar projection of B onto n will be this high. So it's basically a component of vector B that's parallel to n. And notice that that component has the same height as D. So we can say that D is the absolute value of the scalar projection of vector B on vector n. And basically, this is B cosine theta if we do some trig. So let's say this is B. If this is theta here, based on alternate interior angles, if you remember that in geometry. Now, cosine theta is going to be equal to the adjacent side, which let's call that x, divided by the hypotenuse, which is b. So we can see that x is going to be b cosine theta. But we need to use the magnitude of b. So this part here is equal to what we see here, which is the length of the component of b that is parallel to n. So that's the scalar projection of b onto n. So this is how you can find it. But we don't have an angle, so that's not going to work out for us. So let's talk about what we can do. Now, let's say we have two vectors, vector A and vector B, and we know the angle between them. The dot product of A and B is equal to the product of the magnitudes of A and B times cosine theta. So notice that we have this portion of the equation. To isolate that part, we need to divide both sides by the absolute value of A. So we could say that B cosine theta is the dot product of A and B divided by the magnitude of A. Well, in this example, B could be thought of as capital B, and A could be thought of as the normal vector n. So now we're going to have the dot product between n and b. But because we're dealing with distance, we want the absolute value of that dot product. We don't want any negative answers because the distance between a point and a plane should be positive. So this is going to be the dot product of a and b, or n and b, divided by the magnitude of n. So this is the formula that we're going to use to help us get the answer to the question, or to the problem rather. So let's begin with the dot product of n and b. So we have vector b, and vector n is simply a, b, c. So a is 6, b is -3, c is 2. So d is going to be the absolute value of the dot product of n and b. So this is going to be a times x1 minus x0. And then it's going to be b times y1 minus y0. And then plus c times z1 minus z0, divided by the magnitude of vector n, which is going to be the square root of a squared plus b squared plus c squared. Now let's do some algebra. So let's distribute a to x1, b to y1, c to z1. So I'm going to get ax1 plus by1 plus cz1. I'm going to group these together. Next, I'm going to multiply a by negative x0, b by negative y0, and c by negative z0. All of these terms will be negative, so I'm going to take out a negative sign, and it's going to be a x0 plus by0 plus c z0 divided by the same stuff. So let me get rid of this because I am running out of space. Now let's talk about the equation of a plane. The equation of a plane is in this form. It's ax plus by plus cz plus d is equal to 0. But d is on the other side. So to move positive d from the left side to the right side of the equation, this becomes equal to negative d. So I can replace what I have here with negative d because they are equal to each other. Technically, this should be ax0, by0, cz0. So now I have that d is going to be ax1 plus by1 plus cz1. Now replacing all of this with negative d, I have negative times negative d, so it becomes positive d. And then all of that will be divided by the square root of a squared plus b squared plus c squared. So this is the formula that we need in order to calculate the distance from a point to a plane. So now let's work on finishing the problem. So point P1 is what we see here, 3, 7, -4. x1 is 3, y1 is 7, z1 is -4. And a is 6, b is -3, c is 2. D, well, be careful with this one because I should have kept this, but remember the formula. D is on the left side of the equation, not on the right side. So D is not 10, but D is -10. That's one trap you don't want to fall for. So let's go ahead and plug everything in. So A is 6 times x1, which is 3. B is -3. y1 is 7. C is 2. z1 is -4. And D is -10. So all divided by the square root of a squared. So that's 6 squared plus b squared. That's -3 squared plus c squared, which is 2, so 2 squared. 6 times 3 is 18. Negative 3 times 7 is negative 21. 2 times negative 4 is negative 8. And then we have minus 10. 6 squared is 36. 3 squared is 9. 2 squared is 4. 18 minus 21, that's negative 3. Minus 8, that's negative 11. Minus 10, that gives us negative 21. 36 and 4 is 40 plus 9, that's 49. The absolute value of negative 21 is positive 21, and the square root of 49 is 7. So the answer is 3. And that's basically it for this video. So now you know how to find the distance between a point and the plane. You also know how to derive the formula if you really need to know that information.
Next, we look at the angle between a line and a plane.
Hi. Now, in this video, what I want to do is show you how we can work out the acute angle between a plane pi and a line L that intersects the plane. Now, in order to find that acute angle theta between the line and the plane, what we've got to do is imagine taking a point on this line here and dropping a vertical triangle onto the plane. And if we make that triangle a right angle triangle, then the angle theta that we're looking for is this one marked in here. Now, if I take a side view of what I've got here, it's going to look something like this, with our plane pi here, the line L intersecting the plane, and you can see our vertical triangle, this perpendicular triangle here, with the angle theta drawn in. Now, in order to get this angle, we'll be given the equation of the line L. It can come in various forms. It could come in this form, the vector parametric form, or the Cartesian form. And you should be familiar with these forms. If not, do check out video tutorials on this, where you'll find links to these videos in the description below this video. Now, L, M and N in either of these equations represent a vector parallel to the line. And I've called this the vector B. And it's got these ratios L, M and N in, which we should be able to extract from whatever form we're given for the equation of a line. Now, when it comes to the plane pi, the equation of the plane pi can be given in various forms. For instance, the scalar product or dot product form, or the Cartesian form. And you should be familiar with these forms. If not, again, check out the tutorials on this in the description. Now, you'll notice in green I've written A, B and C because these represent the components of a vector, let's say n, which is normal to the plane. And what I'm going to be doing is working out the acute angle, let's say alpha, between the normal n and the vector b, which is the vector parallel to the line. And we can do that very easily by taking a rearranged version of the scalar product or dot product. That is, that cosine of the angle alpha equals the modulus of b dotted with n, all divided by the magnitude of b times the magnitude of n. You'll notice I've got these in a modulus sign because I'm looking at the positive value, which will give us an acute angle for alpha. And then once I've worked out alpha, it's a simple case of just taking it away from 90 degrees, or pi upon 2 radians if you're working in radians, to get the angle theta. If you're working in degrees, then it's just going to be 90 degrees minus alpha. Okay, so I've got a question here which we'll just run through. It's to find the acute angle theta between the plane pi and the line L, where pi has this Cartesian equation, 2x plus 3y minus 4z equals 2, and the line L has this parametric vector form, I minus 5j plus 2k plus lambda multiplied with all of the vector 3i minus 2j plus k. So What we need to establish is a normal to the plane, and that's easy because it's just going to be the coefficients of x, y and z. That would be 2, 3, minus 4. So we can let n be the vector 2i plus 3j minus 4k. And for a vector b parallel to the line L, then it's going to be this vector in here, 3i minus 2j plus k. So I've got that in there. Now I've just got to use this formula here, and you can use it, by the way, as n dot b over the magnitude of n times the magnitude of b. It obviously doesn't matter which way round you do it, as this is commutative. So if I work out cosine alpha, then you can see I've done n dotted with b. 2 times the 3 plus 3 times the minus 2 plus negative 4 times the 1 here. And that's all over the magnitude of each of the two vectors, n and b. And if you use your calculator, you'll find that you get this value here. And this is a classic case where this would come out negative, but because I've put the modulus sign down it, I strip the negative off and I get the positive value 0.1985 and so on. So just take the inverse cosine of both sides, and if you're working in degrees, that angle alpha turns out to be 78.549 and so on degrees. So I just need to get theta now, which is just a case of taking that angle away from 90 degrees, and you end up with 11.5 degrees to 1 decimal place. Okay, so I hope you've been able to get that example. What follows in this series is another example you might like to try, and there's a slight twist in it, so do have a go at it, and hopefully you'll be able to do questions like this.
Lastly, we shall look at the angle between a line and a plane.
So let's begin with a picture. So let's say this is the first plane, and beneath it is the second plane. And then let's say this is the normal vector of the first plane. Let's call that n1. And here we have the normal vector of the second plane, n2. So this angle, that's the angle between the two planes, that's theta, which is the same angle here. In order to find the angle between the two planes, we need to find the angle between the two normal vectors. If we can do that, that's going to give us our answer. So let's go ahead and begin. The normal vector for this plane, let's call it the first plane, is going to be the coefficients of the equation, the numbers in front of x, y, and z. And so that's going to be 2, -3, 4. Now the second normal vector, that's the normal vector for plane 2. It's going to be 3, 5, and -2. So now that we have the two normal vectors, our next step is to find the angle between those two normal vectors. To find the angle between two vectors, we could use this formula. Cosine theta is equal to the dot product of n1 and n2 divided by the magnitude of the two vectors. So let's begin by finding the dot product of the two vectors. To do that, we need to multiply the x values, the y values, and the z values together. So it's going to be 2 times 3 plus -3 times 5 plus 4 times -2. Now the next thing we need to do is divide it by the magnitude of the two vectors. So the magnitude for n1 is going to be the sum of the squares of these values. So it's going to be 2 squared plus negative 3 squared plus 4 squared. Now for the second normal vector, we're going to follow the same process. So we're going to have 3 squared plus 5 squared plus negative 2 squared, all within the square root symbol. 6 minus 15, that is negative 9. Negative 9 minus 8 is negative 17. 4 plus 16 is 20 plus 9, so that gives us the square root of 29. And then 9 plus 25 is 34 plus 4, that's 38. Now let's multiply 29 and 38. So that's 1102. So we have negative 17 divided by the square root of 1102. And so cosine is equal to that value. So now we could find the angle. So it's going to be the arc cosine of what we have here. Negative 17 over the square root of 1102. So go ahead and type that into your calculator. So you should get 120.8 degrees. So this is one of the two answers. So let me explain. Let's say this is one of the planes. And let's say here we have another plane. So this angle here, that's the larger angle, that's 120.8. We also have a smaller angle, which is going to be 180 minus 120.8, and that angle is going to be 59.2. Just think of the intersection between or of two lines. Actually, let me draw a line this way. So this angle would be 120.8, and this other acute angle is 59.2. So that's how we get two possible answers. So that's how you could find the angles between the two planes.